Hello friends. In today's lecture, we will be looking at the computational approach. You may recall when we looked at laminar boundary layers also, we looked at various classical methods, and then towards the end I also introduced you to computational methods and introduced you to CFD. So as a follow-up of that, and as a follow-up of whatever we have learned in the last few lectures about turbulent flows, in today's class we will be talking about how do we computationally solve turbulent flows. All of us may recall that when we started the description of turbulence in the first lecture, I actually talked to you about various different descriptions of turbulence. So we will basically be drawing from that understanding in order to also understand how to model turbulence. The first thing that we need to understand is that in turbulence there are various different length and time scales. This is something that we had talked about in the first lecture. We'll again come back to that in today's class and use that in order to find what is the computational requirements for solving turbulent flows. So, strictly speaking, the Navier-Stokes equations, which basically talk about the conservation of mass and momentum, are completely self-contained and they are adequate to solve for any kind of flows, including laminar and turbulent. So, what's the big deal? Why is turbulent flow so different and why are we so worried about it? The big deal actually comes from the various length and time scales that need to be resolved. So if you want to understand the effect of the eddy motion on the mean flow, basically in Reynolds averaging we saw that we average those fluctuations so that the fluctuations are completely forgotten. And we look at only the mean flow, and the fluctuations appear in one or two terms which contribute to, for example, in the momentum equation, additional viscosity, we called it the eddy viscosity, or in energy equation it contributes to additional diffusivity, we called it the eddy diffusivity. So this is one way of representing the effect of the turbulent fluctuations on the mean flow. But if I want to use the Navier-Stokes equations to solve this, then what we need to do then is to solve the entire set of Navier-Stokes equations so that you are able to capture the fluctuations. And the fluctuations are of various scales, because we looked at the mixing length model where we said that the size of the eddy would be dependent on the distance from the wall, and the farther from the wall, the bigger the size of the eddy. And the eddy basically transports fluid from a distance y plus L to y and back. So this L is basically the length scale of the eddy in that region. Now this length scale in the farthest region from the boundaries where the main motion is there, the large eddies are present, is of the size of the object itself. So if I have a computational domain around, let us say, an aircraft wing or an whole aircraft, then the largest of the eddies that is created by the motion of the aircraft will be of the size of the aircraft itself, right? So the largest eddy is in size comparable to the domain size, the computational domain size. So if you have a computational domain around an airplane, maybe a little more to cover the tail wake region, so it will be, let us say, the computational domain is about 10 times the size of the aircraft. Then the eddies themselves will be of the size of the aircraft itself. So this is one extreme. The largest eddies are of the size of the aircraft or the size of the object that produces these eddies. Right? On the other hand, the other end of the spectrum, where these large eddies then break up into smaller ones, transfer their kinetic energy to smaller eddies, and then they further break up and further break up, until such time that they reach the smallest scales, which is closer to the molecular scales, where viscosity dissipates the kinetic energy in the eddies in the form of heat. This is something that we had studied or we had discussed in the first lecture. So what is the size of those eddies that dissipate the energy in viscosity? Kolmogorov is a Russian scientist. He proposed the theory of cascading of the energy from the highest to the lowest size of eddies. And he proposed, or he identified a length scale by argument of dimensional analysis and various physical understandings, that the smallest size of the eddies are given a length scale, which is often called the Kolmogorov scale. Okay, so the Kolmogorov scale, the textbook of turbulence modeling by Wilcox, which I was referring to for doing this, actually talks about the size of the Kolmogorov scale for a particular flow scenario. So the book talks about the flow past a car which is moving at 65 miles per hour, which is like close to 90 kilometers an hour. So a car, the flow that is going over its windshield when the car is moving at that speed would have a Kolmogorov scale of a certain size, which will be of the order of 10 to the power of minus 4 inches, he says. So if I calculate it in metric units, it comes to the order of a micrometer. So the Kolmogorov scale, typically for flows of that speed, which is typically of the order of about 20 meters per second, right, 25 meters per second kind of velocity, the Kolmogorov scales correspond to. So the Reynolds number, depending on the vehicle size, will be of the order of 10 to the power of 7, 10 to the power of 7, 7.5, that range. So the Kolmogorov scales would be of the order of size, let's say 10 to the power of minus 6 meters. So if I have to resolve the Kolmogorov scale, then I need to have grid size which is smaller than that. So let us say the grid size, delta x, that I divide my domain into, delta y and delta z in the 3 directions, should be of the order of 10 to the power of minus 7 meters. Right. So even if I consider a moderate sized computational domain, not that of an aircraft where I have hundreds of meters of the size of computational domain, even if I look at a 1 meter by 1 meter by 1 meter computational domain with that grid size, that is 10 to the power of minus 7 meters of each direction. So it will be 10 to the power of 7 grid points in one direction, 10 to the power of 7 grid points in the other direction, 10 to the power of 7 grid points in the third direction. So I get 10 power 7 by 10 power 7 by 10 power 7, 10 to the power of 21 grid points. Right? That is a crore. 10 to the power of 7 is a crore, right? So you actually get not a trillion, but 1,000 trillion grid points. That's the size for just a 1 meter by 1 meter by 1 meter grid domain with nothing else happening. It's only flow, right? We are not talking about things like shocks. That is, in compressible flow, you have sudden jump in pressure and velocities when the flow goes supersonic. Then the shocks are very, very thin, and then those gradients and the thermal phenomena that happen in the shocks result in much finer length scale requirements. Similarly, chemical reactions. If there is a chemical reaction happening at the boundary layer or at close to a shock, like in the case of supersonic combustor, in the case of scramjets, which are used in missiles, then you basically deal with scales which are even smaller than 10 to the power minus 7. Right? So we are not looking at them now. So we are just looking at flow. So you need 1,000 trillion grid points in a 1 cubic meter computational domain, okay, in order to resolve the length scales. And talk about time scales, the Kolmogorov time scales. If I look at Kolmogorov time scales, then the Kolmogorov time scale for this kind of a problem is of the order of again a millisecond. Sorry, microsecond, 10 to the power of minus 6 seconds. So if I have to resolve that, then I need to have at least 10 grid points in 1 microsecond. So that is 10 to the power of 7 time steps for 1 second. And if I'm looking at a phenomenon of, let us say, a 15 minutes phenomenon, okay, something that happens over a period of 15 minutes. 15 minutes is about 900 seconds, or let's say 1,000 seconds. So that is 1,000 into 10 to the power of 7 time steps, which is 10 to the power of 10 time steps. So what does this mean? In each time step, I will need to solve 10 to the power of 21 equations for one variable, let us say u. Similarly, I have V, I have W, I have pressure, I have temperature. Okay. So if I have typically about 5 or 6 variables, then I'll have 5 or 6,000 trillion grid points on which the equations are to be solved. So if I construct a matrix for the solution, it will be 6,000 trillion variables to be solved for in a matrix. So 6,000 trillion by 6,000 trillion matrix if it's a full matrix. Fortunately, these matrices are sparse, so you normally get a sparse matrix of that size. So 6,000 trillion variables to be solved for every time step, and you need to go 10 to the power of 10, that is 10 billion time steps in order to get solutions for a 1 cubic meter domain for 15 minutes. So this is the kind of computational requirement for direct numerical simulation. What do you mean by direct numerical simulation? Solving the Navier-Stokes equations to get the effect of the turbulence on the flow. Now, we don't need this much detail in most cases, because in most cases, you are not looking at time scales of the order of 10 to the power of minus 7 seconds or length scales of the order of 10 to the power of minus 6 or 10 to the minus 7 meters, but you actually then eventually need to average these quantities in order to get the quantities of engineering interest, such as wall shears at local locations or averaged, or Nusselt number local or averaged, right? So there is a huge amount of churning that's required in order to accurately capture the shear stress and the Nusselt number on the boundaries. Okay. Or similarly, mixing that happens in free jets or buoyant jets and things like that. So the computational effort for direct numerical simulation, even with the biggest of high performance computers today, is a Herculean task. Okay, because solving 6 trillion equations simultaneously every time step, and solving that for, let's say, even 10 billion time steps is, you just see so many zeros, but the zeros have so much value now. And every zero adds load to it. Because the fastest computers that you might have today might have speeds of petaflops, 10 to the power of 18 operations per second, floating point operations per second. That is still too low for the kind of things that we're talking about, because we are talking about something which is still thousands of times larger than the kind of processing speed that we are looking at. And so you say, okay, for each time step, you have to solve for 10 to the power of 21, 6 into 10 to the power of 21 variables. So 6 into 10 to the power of 21 variables, each variable, if it requires for the solution in one time step, even 10 or 20 floating point operations per iteration and 10 iterations of that kind. So 150, 200 floating point operations for one variable. Then you get to multiply that 6,000 into 200, that becomes 1.2 lakh trillion. So you again get to a quadrillion almost in terms of the number of floating point operations. So even if you are able to do 10 to the power of 18, it will take something to the tune of 10 to the power of 6 seconds, which compares with decades of lifespan of a human being, right? So it's still very far from what is realizable in the case of HPCs even today with such fast computing still available. So now the direct numerical simulation therefore is very restricted in use today. It's only used for very small domains, let's say 1 centimeter by 1 by 1 or 10 centimeter by 10 centimeter by 10 centimeter, for very short durations or for that kind of things, in order to validate models that are produced for turbulence where measurements become difficult, right? So such is the limited usage of DNS. DNS is presently used for validation of models and creation of models rather than actually engineering computations. Okay, so let's move on to the whiteboard so that we can write down something and show you as notes. I will share my handwritten notes with you so that you can appreciate it reasonably. So I'll share that with you, but in any case, let's go to the whiteboard. So computing turbulent flows. So here we talked about the Kolmogorov scales. Okay, so in Kolmogorov microscale, I'll just give you a few expressions which I do not know to what extent it will make sense to you, but you can still look at that. So eta is the Kolmogorov length scale. Kolmogorov length scale eta is given as mu cube divided by epsilon, whole thing raised to the power of 1 by 4. Here mu is the kinematic viscosity. It's a molecular viscosity which is mu by rho. Okay, so this is of the unit of meter square per second. And epsilon is dissipation rate of turbulent kinetic energy. Okay, so this we will come to a little bit later. I'll just introduce you at this moment here. So this is the turbulence quantity and this is the molecular quantity, and the Kolmogorov scale is a combination of the two because you are dissipating turbulence into viscosity here. So this is the dissipation rate of turbulent kinetic energy. So turbulent kinetic energy itself has a units of meters per second whole square, so meter square per second square, and the dissipation rate of that has per second, which is meter square per second cube. This is the units of this. So this eta has the units of meter. You can check that here. This is meter square per second whole cube, which is meter to the power of 6 by second cube, and this is meter square per second cube, so this is meter to the power of 4, and to the power of 1 by 4 is meter. So that is the Kolmogorov length scale. So this for a car at 65 miles per hour, windshield, boundary layer, let us say, the Kolmogorov scale eta is of the order of 4 into 10 to the power of minus 6 meters. Okay, which is basically typically around 10 to the power of 1 to 10 to the power of 2 times molecular mean free path. Okay, in this case it's about 75 times. That's what it was shown. So this is the range that is there. So molecular mean free paths are of the order of 10 to the power of minus 8 to 10 to the power of minus 7 meters. Okay, so this is in the order of 10 to the power of minus 6 to 10 to the power of minus 7 typically. Okay, so that is the thing. And the Kolmogorov time scale tau is given as equal to mu by epsilon whole to the power of half. Okay, and this velocity scale, you can actually divide one by the other. You will get the velocity scale, which will be of the order of mu epsilon whole to the power of 1 by 4. Okay, so this is basically this divided by this. That's what you get here. So these are the Kolmogorov scales of this one, and that determines your grid requirement. So if I have 1 meter by 1 meter by 1 meter domain that I need to solve. So suppose I'm solving for, let us say, the flow around a small toy car, okay, which is actually a laboratory model of, let us say, the car kept in a wind tunnel. Okay, so that is the test section that I'll be solving for 15 minutes, which is about 900 seconds. Okay, so then this grid size, this is 10 to the power minus 6, so if I take as delta x equal to delta y equal to delta z equal to 10 to the power of minus 7 seconds, so that I completely cover this, or it's of the order of 10 to the power minus 7 even, 4, 5 into 10 to the power minus 7 also. And delta t, again of the order of 10 to the power of minus 7 seconds. Okay, so this is meters. Okay, so then we get for this domain, you get 10 to the power of 21 grid points into, let us say, 6 variables. Okay, and this multiplied by, let us say, 15 minutes is about 900 into 10 to the power minus 7, around 10 to the power of 10 time steps. Okay, and if this iteratively takes about 10 to 20 iterations every time step, so that many, and multiplied by, for each iteration, if I have something like 20 floating point operations, that is the number of multiplications and additions that I need to do for the calculation of one particular grid point variable of one value. So that will be the number of computations that you will get. So that will basically become, let us say, this is 20 into 20, let us say 20 into 20 is 400. 400 into 6 into 10 to the power of 21. So that is 2400 into 10 to the power of 21 into 10 to the power of 10. So this is 2.4 10 to the power of 3, 10 to the power of 24, 10 to the power of 34. So it gives something like 2 into 10 to the power of 34 calculations. Okay, and these days we have computers which can go to 10 to the power of 18 floating point operations per second. Okay, this is all the processors and everything put in together. This is petaflops. So if I have, for example, a computer which has 65,000 or 128,000 processors, and each of them capable of certain speed, then you get to this kind of computational operations. Still, you see there is a 10 to the power of 16 factor. So 10 to the power of 16 seconds is what you are looking at. That will be way beyond the lifespan of a human being, because one day is something like 0.8 10 to the power of 5 seconds, right? 86,000 something seconds. So you can see 10 to the power of 16 would be, even if I take 10 to the power of 5 out, there will be 10 to the power of 11 days. Okay, so that is way beyond what a human being can think of as a lifespan. Okay? So that's the reason why we are saying that it's just not in the real realm. And I'm still talking about 1 cubic meter and not the flow around an aircraft, which can be like 50 meter by 50 meter by 100 meter, right? Because the wingspan of an aircraft is typically about 35 meters. So even if I extend the domain to twice that size, it will be like 75 meters on the sidewise. So it will be like 75 meters by, let us say, height is like 30 meters or 40 meters, and then the lengthwise you go to something like 200 meters, because you need to at least cover some length of the aircraft. So basically you are talking about sizes which are again a few 10 to the power of, so 10 to the power of 4 or 10 to the power of 5 times this number, right? So that will be, you can just forget it. Okay, so that's the requirement for DMS. So direct numerical simulation, therefore, is definitely not an option for engineering problems. So we'll need to look at alternatives. So what is the alternative? So let me just come to the Kolmogorov theory a little bit in order to explain that a little better. So Kolmogorov actually talked about the spectrum, energy spectrum, So in turbulence, what we talk about is that the big eddies, they actually break up to small eddies, and they break up into even smaller eddies, and they break up finally to the molecular scale, and that is the way the dissipation happens. So if I look at the scale of this in the inverse form, so the wave number is actually the number of oscillations per unit length. Okay, so if I call this as kappa, okay, so the higher the frequency, the higher the wave number, because the smaller the waves, so higher the wave number. So your molecular scales would come somewhere here, and the length scale of the flow would come somewhere here. So if I call this as L, and if I call this as, let us say, eta, which is the Kolmogorov length scale, so this is L inverse, this is eta inverse, and there would be something called a lambda inverse here, which I'll talk about as Taylor microscale. So what has been found is that if I say what is the amount of energy that is present in the eddies of that size kappa, with the size kappa on the, this kappa is different from the von Karman constant that we looked at. This is basically the wave number. Okay. So the number of oscillations created by these eddies per unit length. So these will have very few, so the small wave number. These will have very large, so the high wave number. So what is found is that the spectrum looks something like this, then it becomes a straight line in this region, and then it goes like that. So there is a kappa to the power of minus 5/3 slope that you get in this region from the Taylor microscale to the Kolmogorov microscale. After that, so if you draw lines here, then this is a large eddies. This is usually called the inertial subrange, and this is called the viscous subrange. Okay. Now, whatever is on this side of the Taylor microscale, I'll come to what is Taylor microscale. So this is Kolmogorov. This is mean free path. Okay. And this is Taylor microscale. And this is the object length scale or domain length scale. Okay. So the eddies that are of size larger than the Taylor microscale, which is to the left of this side, they depend on the geometry or the object which is causing the thing. So if it is an aircraft, it produces a certain kind of wakes or eddies. Then if it is a car, it produces another kind. If it is a turbo machine, turbine blade, it produces a different kind, and so on. So the eddies on this side depend on the object or the geometry. But what Kolmogorov found is that the energy spectrum on this side is, that is the inertial subrange and the viscous subrange, are reasonably universal. Okay, so inertial and viscous subrange are universal. What does it mean? It means that irrespective of what is the production mechanism for these eddies, the way they transact energy from the large eddies to the medium-sized eddies and the medium-sized eddies to the small eddies, which happens in the inertial subrange, and the small eddies to heat in the viscous subrange, this mechanism is more or less the same irrespective of whether the wakes are produced by the aircraft or turbine blades or automobile or any such source, or be it even atmosphere, any mechanism that produces the large eddies, whatever is on the right side of lambda here are universal, which basically means that they don't depend on the object that produces the grid. So then what this says is that from the Taylor microscale upwards is what you need to actually calculate using CFD, and what is on this side can be modeled reasonably accurately, because the model is going to be the same for whether it's a flat plate boundary layer, whether it's a flow past a sphere or cylinder, or whether it's a flow past an aircraft, whether it's a flow past a blade, or whether it's a flow inside a pipe. Whatever is the flow, the mechanism for this side is going to be the same, so you can make measurements in simpler geometries and simpler cases and prepare the model and use it for complex cases. So what it says is that spatially the larger grids or the larger volumes will need to be computed, and the smaller size can be using simpler models for representing them. So this concept gives rise to what is called the large eddy simulation. That is, x or delta x larger than lambda need to be resolved by the computational grid. And less than this can be modeled. So you have a grid size which is comparable to lambda. Okay. I'll tell you what that lambda is. So if you have a grid size that is comparable to lambda, and then you use the spatial averaging, so instead of the Reynolds averaging which we did as time averaging, you do a spatial averaging or spatial filtering. This is called spatial averaging or filtering of the Navier-Stokes equations, so that you get what is called the filtered Navier-Stokes equations or the large eddy Navier-Stokes equations, which are spatially averaged Navier-Stokes equations, which don't contain the smaller sized frequencies or the higher frequencies, but it has the lower frequencies corresponding to lambda or larger length scales. So then you solve them using the partial differential equations, and then whatever is happening inside the grid, the terms that come because of filtering in this one, just like the Reynolds stress terms that you get in your time averaging, you will get the filtered terms, the u prime, v prime terms which are filtered out. So you take the average over space, let us say 0 to xp of u dx, okay, and this you call it as u bar into xp, right? And then you say u then will be equal to u bar plus u prime. This u bar is usually written in the form of u like this. This is the filtered u. So this is the u plus u prime, and you normally write it as a u double prime in order to distinguish it from the Navier-Stokes, the Reynolds average Navier-Stokes. So this is u is equal to averaged u plus the fluctuating u. Now this fluctuating u and its effects, that is the combination of u double prime, v double prime, and u double prime, t double prime, etc., they are modeled using what is called the subgrid scale modeling. Okay, so whatever is larger than the grid is simulated, so it is called a large eddy simulation, and whatever is smaller than the grid size is modeled using what is called the subgrid scale or SGS modeling. Okay, so this is how the computations are done. Now this seems to be good news, because you don't need to go to DNS sizes, but you can actually work with the sizes which are bigger than DNS. But how much bigger? So the Taylor microscale lambda has been given some figures in the book by Wilcox. I'll give you the reference. Wilcox, Turbulence Modeling, Turbulence Modeling for CFD. This is a classic textbook which talks about the turbulence and its modeling. Okay, so in that we get this. So the lambda divided by eta is usually of the order of Reynolds number to the power of 1 by 4. This is the thing that we get. So if we are looking at RE, this is Reynolds number with L as a length scale, which is the object, or the object size as a length scale. So if we are dealing with RE of the order of 10 to the power of 4, this is 10, right? And if you are dealing with RE of the order of 10 to the power of 8, this becomes 100. So you are in the range of lambda is equal to 10 to the power of 1 to 10 to the power of 2 times eta. And this eta we said is of the order of 10 to the power of minus 6 meters. So this fellow will be of the order of 10 to the power of minus 4 to 10 to the power of minus 5 meters. It's not a great advantage in terms of just one linear dimension, but if I look at the cubical dimension, so if I take a 1 meter by 1 meter by 1 meter domain again, so then you need, this is 10 to the power of 4 to 10 to the power of 5. So if I try to resolve it in that range, so you will get a 10 to the power of 12 to 10 to the power of 15 grid points. So your work is now 1 million times smaller. And if I take the time scale also to grow with the length scale in the same fashion, because your velocities are of the similar order. So if I can look at velocities as the length scale divided by time scale, so you will get a lambda divided by the tau Taylor. So under this tau Taylor, so if this is of the same order, this is also of the order of eta by tau Kolmogorov. So now this, if this is 10 to the power of minus 6, this was 10 to the power of minus 6. So if this is 10 to the power of minus 4, this will also be 10 to the power of minus 4. So you will get for 15 minutes, you will get 10 to the power of 4 into 10, so it will be 10 to the power of 7 to 10 to the power of 9 time steps. So then the overall number, if I try to look at it, it will become something like 2400 multiplied by 10 to the power of, I'll take the larger of these, let's say 10 to the power of 15, and the smaller of these, so the larger of these is 10 to the power of 9, okay, or the other end is 2400 multiplied by 10 to the power of 12 into 10 to the power of 7. So this is again 3 plus 15, 18 plus 9, 27. So this is 2.4 into 10 to the power of 27. And this is 3 plus 12, 15 plus 7, 22. This is 2.4 into 10 to the power of 22. So from 10 to the power of 34, we have come between 22 to 27. So we have come down by 10 to the power of 15 orders. So it's not a small change, because we saw that here it's only 10 to the power of 1 to 10 to the power of 2, but this change is substantial. So now this, you can imagine, suppose this is 10 to the power of 22 and you are dealing with 10 to the power of 18 floating point calculations per second, it is still within striking distance, right? So you can still do it in the order of something like 10 to the power of 4 to 10 to the power of 5 seconds 10 to the power of 10 to the power of 4 to 10 to the power of 5 seconds of computation, which will be still a tractable number. 10 to the power of 5 seconds is 1 day, right? Because 86,400 seconds is 1 day. So you can still see that the smallest of these problems can still be solved in LES in about a day if I have the fastest of the computers in the world. And if I have to get here, then it will go to something like 10 to the power of 5 times, or 10 to the power of 5 days, which is still intractable. Okay, so the largest of LES problems are still not quite tractable, but the smallest of LES problems are still reasonably tractable to solve, right? So you can say that the larger dissimulation gives you a workable substitute for at least the simplest of the turbulence problems, engineering turbulence problems in computation. Okay, so this is the large Eddy simulation. So these are the two methods in which you try to capture the entire statistics. Okay, because your turbulent fluctuations are always 3D and transient. Okay, and you compute all the flows as 3D transient flows, irrespective of whether your computational domain is two-dimensional or your flow being steady. The turbulent flows will always be calculated using 3D transients, and that is the reason why the LES and DNS are very expensive. Okay, so that brings us then to asking the question, can we do it in a more simple manner? Do we really need to go for large Eddy simulation or direct numerical simulation? The good news is that in most engineering problems, we don't need the spectrum. We don't need the energy spectrum of turbulence. We don't need the turbulent fluctuation details. But what we need is the net effect of the turbulent fluctuations and the averaged values of shear stress and heat transfer. And more often than not, they are steady state systems. That is, the mean flow is steady. The fluctuations may be transient, but you don't need to worry too much about them. In which case, then we go into modeling of turbulence. In modeling of turbulence, primarily we use averaging. Okay, we had studied about Reynolds averaging or time averaging. That is, you said you integrated between 0 to some time period Tp dt gives me Tp times u bar. Okay, so this is my thing that I used. So 1 by Tp going here, I get u bar is equal to 1 by Tp integral from 0 to Tp of u dt. So this is something that we get, and then we write u is equal to u bar plus u prime, and we calculate quantities pertaining to u bar and model quantities pertaining to u prime. This is what we had done in our understanding of Reynolds averaging. So this is one averaging that is commonly practiced, but Reynolds averaging will not work for variable density flows. So you go to what is called the Favre averaging. Which is actually density weighted averaging. Because your density itself will be rho bar plus rho prime in some fashion, and u will be u bar plus u prime in some fashion. So the u bar, if I am evaluating it without the density, it's not going to be of much use. So what I do is I integrate rho u dt from 0 to Tp and divided by integral from 0 to Tp of rho dt. Okay, so this becomes my u bar, and this is called the density weighted averaging or Favre averaging. So in the same way I do for other quantities, and then I write u is equal to u bar plus u prime and so on. So this becomes what is called the Favre averaging, and this is important to do where density is not constant. So there are many flow situations where density is not constant. So for example, there is flows of multi-component systems, flows of non-isothermal systems where buoyancy is important, and so on. So the density weighted averaging becomes an important quantity. A third kind of averaging, which is also practiced, is what is called the ensemble averaging. This is basically for periodic flows. what is a periodic flow? Say for example, if I'm looking at a turbo machinery, okay, so I have a number of blades here, and when this is rotating, if I'm measuring the velocity at one particular location, what will happen is there will be a time period from here to the next blade crossing over and going to the same position. So this blade goes from here to here, then there is one time period that is gone. So then the next blade, this blade going from here to here will be another position. So if I measure at the same location as a function of time, I'll get a periodic variation in velocity in which I'll have fluctuations. So if I measure this quantity for thousands of such revolutions and average it, then I get a U bar, which is the average of the instantaneous velocities here corresponding to the same positions of the blades thousands of times. Okay, so if I do that, then I get an ensemble averaging. So U bar plus U prime will be equal to U again, where this U bar is actually average over thousands of periods of this. Similarly, in IC engines, so wherever there is a periodic repetition and one particular instantaneous quantity can be measured over hundreds of thousands of similar cycles and then averaged, you use what is called the ensemble averaging, because in this kind of systems, time averaging is a thing which will not work, and therefore you use ensemble averaging. Otherwise, you get very, very small time periods for the time averaging, which will not be an accurate thing to do. So ensemble averaging is something that is practiced in this one. In ensemble averaging also you have density weighted. So in this one, where the flow density is variable. So for example, if I'm looking at a water turbine, I can do without density weighting because the density is reasonably constant. But if I'm looking at a gas turbine or a steam turbine, then I will need to do the velocity averaging or pressure averaging using the density weighting method that I have shown you in the previous slide, and therefore you do what is called the density weighted ensemble averaged equation or the DWEA equations. Okay, so this is the averaging process by which you split the velocity into the mean component plus the fluctuating component. Okay, so U plus U prime, U bar plus U prime, V bar plus V prime, plus similarly W bar plus W prime, P bar plus P prime, T bar plus T prime, and so on. So all the quantities that are there can be split into mean and the turbulent fluctuations. These mean quantities can have their own conservation equations in which these fluctuating quantities appear as additional terms, just like we derived the boundary layer equation for flat plate for turbulent flow, and we obtain terms like rho U prime bar with a minus sign minus rho U prime V prime bar, and you get minus rho U prime T prime bar, and so on. So this kind of terms appeared. Similarly, when I try to derive other kinds of equations, say for example, I would like to derive an equation for K, which is half of U prime bar squared plus V prime bar squared plus W prime bar squared. Okay, so if I want to derive an equation for K, then I will need to get an equation for U prime squared, V prime squared, W prime squared, add them together and constitute an equation for K. Then you get multiple kinds of averaging processes also. Similarly, you also get the second moment closures when you get epsilon, which is a dk by dt term. So derivative of this with respect to time once again. So actually you get various multiple terms, and each of them basically a combination of either 2 or 3 such fluctuations in one averaging, and they need to be understood as to what their physical role in the equation is, and accordingly a model term in terms of the mean quantities will need to be assigned. So that is something that is need to be done. So that is what we call as a turbulence modeling. So first thing that we do in these turbulence modeling is to average the equations, and construct the equations of conservation for momentum and energy in terms of mean quantities, and they contain additional terms which involve this. These are actually modeled as in one set of models, they are modeled using nu t multiplied by del u bar by del y, alpha t times del t bar by del y, and so on. This is something that we saw. These are called the Eddy viscosity models. So you model these terms as additional diffusion terms which have a diffusivity called alpha t or nu t, and modeled using del t by dy, del u bar by dy or del t bar by dy. So you say that these stresses or these fluxes are also proportional to the mean velocity gradient or mean temperature gradient, right? So that is one way of modeling, which is called the Eddy viscosity models. Okay, so these Eddy viscosity models basically assume that whether the fluctuation is in this direction, or in this direction, they cause the same value of nu t. So the eddy viscosity caused by the fluctuations in x direction, let us say, y direction and z direction, result in the same value of nu t. So they assume isotropic turbulence. Okay, so the turbulent fluctuations are assumed to be the same in all three dimensions. So it is assumed to be isotropic. This is a very restrictive assumption, because most turbulent flows are not isotropic. For example, even the turbulent flow past a flat plate, suppose I have a flat plate which is a two-dimensional entity like this. So this is the y direction, and this is the x direction, and this is the z direction. Then we know that the fluctuations in the x directions will be substantially bigger, the fluctuations in the y directions will be smaller, and the fluctuations in the z direction will be somewhere in between the two. Okay, so this itself is not going to cause the same kind of diffusion in the x direction, y direction, and z direction. So this is the simplest of flows. Okay, what causes an isotropic turbulence is probably a grid. Say for example, if I have a wire mesh through which a turbulent flow leaves, and there is all eddies which are of very similar size to the size of the mesh that are formed here. In this region, the flow will be isotropic, the turbulence will be isotropic. But other than the grid turbulence of this kind, everywhere else the turbulence is going to be non-isotropic. So the criticism of Eddy viscosity models is that they are not supposed to be working well for non-isotropic turbulence, but they should be good only for isotropic turbulence. And most of their constants are actually evaluated from examples either of isotropic turbulence or of boundary layers, flat plate boundary layers. The measurements there are used for evaluating the model constants in the Eddy viscosity models. So in engineering, we apply these Eddy viscosity models for all kinds of flows, isotropic as well as non-isotropic turbulence, and they seem to be giving reasonably acceptable results for engineers, but for a purist person on turbulence and fluid mechanics, these results are way far away from the correct results. But engineering is very tolerant to that kind of results, so we do accept it. So Eddy viscosity models are popularly used in engineering, although from the pure turbulence point of view, they are not supposed to be accurate models. So what is more accurate is another kind of models called the Reynolds stress models. So what is the Reynolds stress model? In the Eddy viscosity, the Reynolds averaging of equations, for example, if I have a three-dimensional flow, I would be getting 6 quantities: rho u prime square bar, rho u prime v prime bar, rho u prime w prime bar. Okay. Then you get rho v prime w prime bar, rho v prime squared bar, and then you get rho u prime w prime bar. Okay, so there are 6 terms which appear in Reynolds stresses in a 3-dimensional case. And if I have energy equation also, then I'll have a rho u prime t prime bar. Okay, then you have a rho v prime t prime bar and a rho w prime t prime bar. Okay, so 3 different turbulent diffusion of energy terms. So these are again called Reynolds stress terms, but they are the Reynolds flux terms actually, and these are the Reynolds stress terms in the momentum equations. So now if I have to solve for a 3-dimensional flow in which I don't want to assume that these result in isotropic conditions, then I'll need to solve for these 6 plus these 3, a total of 9 extra unknowns. Okay, so you don't use the eddy viscosity model or eddy diffusivity model, but you solve for these separately. So you will need to derive equations for each one of these quantities. Okay, and then you solve those equations. So they are called the Reynolds stress models or the RSM. So these capture the non-isotropic nature of the flow more accurately, but then the effort involved is a lot more. Okay, but there is a whole class of models that have been developed using this, and people do use these models, but these models are not as popular as the eddy viscosity models. So the other class of this is the eddy viscosity models. Where you write rho u prime v prime bar is mu t into del u by del y, del u bar by del y. Okay, and you also use the same quantity in with different mean gradients in the other directions as well. So you rho u prime bar would be mu t times del u bar by del x, and so on. Okay, so you use these things to derive the various quantities, and with that you use the same nu t, and so the only extra thing that you'll need to specify in the whole equation would be this nu t, and you'll need to use models to specify this nu t. So that is why it is called the eddy viscosity models. There is a whole variety of eddy viscosity models depending on the way you specify this nu t. If you recall the way we defined this nu t, we defined this nu t as something which is proportional to L squared in and del u by del y modulus. This is something that we had derived in one of the earlier classes. So this basically has dependence on a velocity scale and a length scale. These two scales will need to be specified in order to define the eddy viscosity correctly, right? So this velocity scale and length scale are specified using different methods, and that gives rise to a whole variety of eddy viscosity models. I'll quickly mention them and stop here. I will not go into details, but just to give you an overview, if I specify the velocity scale and length scale using partial differential equations or ordinary differential equations or algebraic equations. These are the various ways in which we do, and not directly but indirectly. Say for example, the partial differential equation could be for k, which is actually equal to half of u prime bar square plus v prime bar square plus w prime bar square, and in isotropic turbulence this u prime is equal to v prime equal to w prime, and therefore these quantities are equal, so it gives me 3 by 2 u prime bar square. Okay, so u prime is of the order of 2 by 3 k square root of. Okay, so this is the way you represent the fluctuations velocity scale of this. So k would be an indirect representative of the velocity scale that is required to be specified. Similarly, this length scale could be specified using different terms. One is the epsilon term, which is the rate of dissipation of this turbulence, and then you find out if I have a certain amount of energy k and certain rate of dissipation epsilon, what will be the length scale over which this dissipation will happen, and then you get a length scale which is k to the power of something divided by epsilon. So that would give you a length scale. So you see that these are the ways in which the scales are specified, and you may calculate this k and this epsilon, or in place of epsilon there can be a certain term called omega, which is the volumetric dissipation rate, which will be epsilon per unit volume or something like that. So by specifying different quantities such as k or epsilon or L itself directly, you get different kinds of these equations. Okay, and depending on how many partial differential equations are solved, they are classified. So if I solve 0 PDEs, so all scales U prime and L specified algebraically, then you get what is called the zero equation models. So you say, whenever you say this number of equation models, they are all eddy viscosity models of some kind. Okay, so this is zero equation model. Then you have half PDE. What is a half PDE? It's actually a 1 ODE. You can just okay, so it's because it's an ordinary differential equation and not a partial differential equation, it's called a half equation model. So you get half equation models. So usually you express k as a function of y in the boundary layer and use that. So that is a half equation model. One equation model. In one equation models, you either solve for the turbulent kinetic energy k, or there is one class of models where you directly solve for nu t. I'll mention the name of this model because this is a popular model. It's a Spallart-Almaraz model. Okay, and there are many models which use k alone as this one and specify the length scale L using algebraic equations. So then you get what is called the one equation models. The most popular two equation models are the most popular eddy viscosity models are the two equation models. In two equation models, it is always one of the equations is for the turbulent kinetic energy k. What is the turbulent kinetic energy? It's basically the kinetic energy of fluctuations of the flow, which is derived from the mean flow and eventually dissipated in the viscous scales. So you will have a conservation equation which will have source term for this k, that is coming out of viscous shear and buoyancy and all those terms in the mean flow, and then transportation, which is advection and diffusion of k using the advection term and diffusion term, and you will have a dissipation term in the form of epsilon or omega, which will take care of destruction of k in the viscous end below the Kolmogorov scales. So you will have a conservation equation for k, which is a PDE, and you will solve for that. And the second equation can be in one of these variables. One is L, the length scale itself. There can be equations for L or k into L. There are k, KL equations also. Second, otherwise it can be of epsilon, which is the dissipation rate of k. So if k is in meter per second whole square, then you get epsilon is k per second, which will be meter square per second cube. This is something that we also saw when we were looking at the Kolmogorov scales. And the third will be omega. So it will be a k omega model or a k omega model. So omega is volumetric dissipation rate, turbulent kinetic energy. So it will be in terms of meter square per meter cube second cube. Okay, so something of this order. So that will be the kind of dissipation equation that you get for omega. Okay, and so you solve for k omega or omega as a second equation. So the combinations of these makes a large variety of these two equation models, and you get the k epsilon model, the k omega model, k omega model, KL model, KL model, and so on and so forth. And in that also there are multiple variants which actually arise out of different theories that need to take care of. For example, the standard k epsilon or k omega models, they deal with fully turbulent boundary layer core of the turbulent boundary layer, and then from there you derive the model constants and solve for it. But then if there are flows in which the flow is partly laminar in some places and partly turbulent, or wherever the flow slows down, the turbulence reduces in that area. So if you need to capture that, then you use other kinds of models called the renormalization group, RNG. So there is a renormalization group theory in turbulence which basically captures how when the flow goes from high speed region to a slightly relatively lower speed region, whether it regains some level of laminarity, which basically means that the NUT decreases as you go into the lower velocity regimes. So that is the RNG, or sometimes called the realizable. So RNG and realizable k epsilons are variants of the standard k epsilon model. Similarly, you have shear stress transport. Just like we had this Reynolds stress transport models, you have some shear stress transport theory added to this k epsilon, so you will get a SST k omega, which is shear stress transport k omega. So you have various different variants of these models. Some of them are applicable only to free shear flows or non-wall bounded flows, but are also applied to wall bounded flows with some compromise, and some of them are more suitable for recirculating flows or adverse pressure gradient flows and so on. So you find a whole variety of those models. So the common thing about all of these models is that the average terms, that is the mean terms, are solved using the equation, and fluctuating terms are always represented using an approximate model. Okay. Well, I'll close this lecture talking a little bit about boundary conditions of these flows. So boundary conditions are normally applied in these cases by using what you specify at the first grid point away from the wall. Okay, so at the wall this has to have a zero velocity, but specifying this as zero velocity and specifying some viscosity here would actually make the wall shear stress incorrect. So normally nothing is specified at this point. The zero velocity here is inconsequential, but you specify this in such a way that the shear stress at the wall, tau wall by rho, is correctly captured by this. So in order to do that, what you try to do is to keep this in the buffer layer, because we know that the tau wall by rho remains reasonably constant in the near wall region, and after that it goes to 0. So the laminar sublayer and in the buffer layer this remains reasonably constant. So if I put the first grid point in the buffer layer and specify the velocity gradient here using q plus equal to 5.5 plus 2.5 log y plus, which is the buffer layer velocity profile, and using that you determine the tau wall by rho, which is the u star that you get here, then you can actually specify, so you specify the u plus in terms of y plus and calculate the u according to that in the first grid point, then your wall shear stress is correctly modeled. So this is what we call as the this is the law of the wall. and the boundary condition specification using the law of the wall is normally called the standard wall function models. So what this requires is that the first grid point has to be in the buffer layer. So the y plus of first grid point should be greater than 11.6 for this one, because this is in the two-layer model of Prandtl. When I take the laminar sublayer and buffer layer and equate these two, I get it at 11.6. But strictly speaking, typically of the order of 30 is what is recommended for the first grid point distance from the wall. Okay, so you cannot have the first grid point closer than that to the wall if you're using a standard wall function. Okay, there are other models which use what is called the enhanced wall function, which accounts for the viscous sublayer. And in such a case, you basically have to specify that the wall velocity is 0, but the first grid point has to have a y plus should be of the order of 1. Okay, so your viscous sublayer should have at least 4 or 5 grid points in it, so that your no slip condition, v is equal to 0 here or u is equal to 0 here, is correctly respected, and the enhanced wall function captures the wall shear stress correctly. So this is also used in some of the models, and some of these models actually, like for example the SST K omega, should have an enhanced wall function and is not compatible with standard wall function. So you need to look at each of these models and their corresponding compatible boundary conditions, and accordingly use the boundary conditions. So these wall functions are typically used to calculate the near wall u value, and accordingly also the k and the epsilon values. The k and epsilon values in the fully turbulent region, we take that when the velocity is close to the wall, in the near wall region, the velocities close to the wall are pretty close to 0. Then you say that the rate of production of kinetic energy is the same as its dissipation. So you call what is called the equilibrium models, and they are used to determine the relative values of k and epsilon near the wall. So that is how you specify the boundaries. Okay. So with that, I'll close this lecture, because for a preliminary lecture, talking about it more than this may not result in much better understanding, but might result in more confusion. But whatever I have said so far, I think should be in a position to at least take you through the use of these CFD software with a certain amount of background. And so before you click any choice of model, you would at least remember that there is something of this kind that was told in the class, and you would go about and read its theory with a little bit more confidence and use the correct alternative. So in order to be able to use turbulence modeling in Kansas Fluent, when you go about to use it, please remember this, so that you don't make mistakes that are completely ignorant and grave. So I'll stop here, and we'll see again in the next class with the next module on internal force. Thank you.